stellar populations. He did his PhD in Geneva, in Switzerland. Then he moved to Australia, to the Mount Stromlo Observatory for a postdoc. Then he went to Harvard for a postdoc, still working on Cepheids. And then he moved to the Space Telescope Institute, now focusing more on GRBs. And then he moved to Liverpool. He's here because he was observing in La Palma with the wide-field camera at INT. And he was doing some observations of M33 in order to study double-mode Cepheids, in order to study the metallicity gradients in M33. So, and we have him here to talk about the GRB and supernova connection. And so thank you very much for being here.
Well, thank you very much for the invitation. I'm going to, early on, I'll show a little bit what gamma ray bursts are about, and I'll describe a little bit how this connection between supernovae and GRBs came about. But in the second half of the talk, I think it's more going to be a case of, well, how science is made. As you will see that there are several chapters to this story, and a few years ago, at least in 2003, when we became really sure that there was a connection between GRBs and supernovae, this talk would have been very different from what it is now, and particularly near the end, you will see that there has been recent development that force us to perhaps revise either what we think about we know about supernovae or about gamma ray bursts. So first, a few general facts about GRBs in general. They were detected a bit by accident by satellites that were monitoring the Earth for nuclear explosions. And of course, since it was military, it wasn't disclosed immediately, but at some time, soldiers managed to convince themselves that it was completely extraterrestrial. It had nothing to do with the Soviets doing something they were not supposed to do. So they said, well, let's give that to the astronomers. And this is this paper here, Clevesadel in 1973, which was in APJ, the release of that information. And from then on, people have been aware of gamma ray bursts without having any clue as to what they could be. An important development came in the late 90s, late 80s, late 90s. But to show you what a GRB is actually in the gamma ray sky, this image on the left is the whole gamma ray sky, and this is the light curve, basically the number of counts per second. And suddenly you see that at its peak, the whole the sky becomes completely dominated by the GRB. It's like if you're an optical astronomer, you're observing in nighttime, and instantly the sun is above the horizon for a few seconds. That is what happens in the gamma ray sky. And that's one reason why they are, in a sense, fairly easy to discover. They are not all that bright, but many of them are very, very bright. One reason is that the gamma ray sky is actually very faint. So, okay, there is a wide variety of light curves had been noticed for a long time, and I show here just a few examples. In all these plots, the horizontal axis is time, the vertical axis is essentially the number of photons per second. You see that some, like the one here on the right, is very smooth, and it lasts for tens of seconds, or you can have light curves like these that have a lot of substructure. They can last for hundreds of seconds. Here you have 0, here is 300 seconds. This one you have 0 second, here 1 and 2 seconds. So all the action happens basically within 1 second. So they can be very short, they can be very long. Some are very bright, like this one or this one on the right. Some are pretty faint, and you need to seriously bin the data to actually detect them. But one important fact is that very often we see substructure on very short time scales in those light curves, and that if on time scale as short as millisecond, that has an important consequence. It means that the region that is responsible for emitting this light is actually very small. If it's a millisecond, if the structure is a millisecond, it basically means that the emitting region has to be about a millisecond light across, meaning that it's of order a few thousand kilometers. So without knowing anything about GRBs, we already know, about any physical model, we know that one constraint will have to be that they should be the progenitor, the beast, if you want, the engine, whatever it is, at the heart of the GRB has to be very, very small. Okay, it's not a whole galaxy. Now, in the late 80s, the Compton Gamma Ray Observatory was launched, and that provided a number of very important clues as to what GRBs can be. The BATSI experiment on this satellite detected several thousand GRBs. An important result was that they are pretty much everywhere on the sky. They are really distributed isotropically, and it doesn't depend on the brightness. If they were, for instance, that means that some models of GRBs are immediately ruled out. For instance, if you want to associate GRBs with pulsars or with massive OB stars, well, immediately this is ruled out, because we should see the signature of the Milky Way, of the galactic plane in this distribution. It's not there. So either GRBs are very, very close, or they are very, very far. And for a while, there has been two camps regarding the origin of GRBs, either cosmological or very close. Another very important result from BATSI is the fact that there are actually two populations. Oops, I'm going too fast. And this is a plot of the duration of a GRB versus the spectral hardness, which is, for an optical astronomer, it's essentially the color. And there are really two groups. One that we call not very originally long GRBs, and the short GRBs. And the dividing line is around 2 seconds. So if you see a GRB that lasts 2 seconds, we're not really sure whether it's short or long. There are other indicators that allow to classify them. Obviously, the spectral hardness, but there are yet other things. But there are GRBs where we can't really be sure of what they are. What this means is that we're probably going to need to find two types of mechanism of progenitors to produce these two case degrees of events. And as you see, at least for BATSI, the majority of the GRBs are long. It depends on the instrument that is used to detect them, but roughly 3/4 of GRBs are long, and 1/4, or perhaps even less, are short. And what I'm going to talk about in the remainder of this talk is about long GRBs. Short GRBs, there has been some progress made in the last few years, and I can say a few words at the end if you ask me about where we are in this respect. But for this GRB supernova connection, it is really related to the long GRBs. Now, for a long time, gamma ray bursts were found, but all we knew is that a satellite had seen a burst, a flash of gamma rays, and could locate it to an accuracy on the sky of order a degree or a few degrees. And even if the satellite can transmit that information to the ground to astronomers who can point their telescopes to it, to that direction, a few degrees is pretty hard. There aren't so many instruments that are sensitive enough and that have the field of view big enough to search for a possible counterpart at any wavelength right after the alert. So for a long time, because of these large error boxes, there was very little science done on GRBs. People were trying to chase these gamma ray bursts from the ground to find a counterpart. If it's shining in gamma rays, perhaps it's shining at other wavelengths and it's shining for a longer time. But that meant that there was an awful lot of models. And back in 1994, there was well over 100 models, somewhere small modifications of another one. But it went from basically a cosmic ray hitting a dust grain in the solar system all the way to the explosion of a very massive star, the very energetic explosion of a massive star at cosmological distances. And you had everything in between. One particular model had made a prediction, which is what we call the afterglow. It means that there's going to be a gamma ray burst. A physical mechanism will be responsible for the burst, but that burst doesn't happen on its own. There will be long-lasting electromagnetic radiation after the burst, and long-lasting it depends on how sensitive your instrument is, but it can be hours, days, perhaps even weeks, depending also on what wavelength you work. And so people were trying to chase these afterglows, and after that prediction of this particular model, finding an afterglow would actually have been a vindication of this particular fireball model. Eventually, it did happen. And in 1997, where the watershed event is a burst that came about in February, so GRBs are named even less originally than supernovae, where we give them letters. For GRBs, it's just 970228, which is its birthday, 28th of February, 1997. And so that day, a gamma ray burst detected by the Italian-Dutch satellite Bepo-Sax. They found that a few days later, they found a very bright source in the X-ray. And a few days later, that bright source had gone, or had faded significantly. Now, what that satellite could do, what Bepo-Sax could do, is to send positions that were accurate not to a few degrees, but to a few arc minutes. And if you have an optical telescope, a few arc minutes, that's easy enough. Still, you have to look for a possible new source in a field of a few arc minutes. But that's becoming humanly possible. It's not a few degrees where you can have an awful lot of objects. So within that field of view, it is becoming possible to hunt for an optical afterglow. And indeed, that's what people found. And if you need to know where the afterglow is, well, you just follow the arrow, and it will tell you. Again, the same happened in the optical. On the 28th, there was a source here in these observations done at WHT, and a few days later, that source was gone. So a GRB goes off, and in that error box of a few arc minutes, there is an X-ray source that is fading. There's an optical source that is fading. Well, this is very, very likely to be the optical afterglow of this gamma ray burst. So what this means is that from that point on, we're able to find electromagnetic radiation at other wavelengths from gamma ray bursts, but we have a chance of at least getting a spectrum. If we get there early enough, if it's fading, if it's getting fainter and fainter, if we get there early enough, maybe the object will still be bright enough that we can get a spectrum, and we will know what type of object it is. Is it a supernova? Is it a flare star? Or is it anything else? We don't know. At least a spectrum will tell us something about the physical nature of the object. And that came a few months later, where for this burst, people got this spectrum. This is a fraction of the spectrum. And those of you who measure spectra of distant objects, you will see several lines that correspond to this redshift, about 0.8. So immediately, the first GRB that had its redshift measured, it's 0.8. So right away, problem is solved. They are at cosmological distances. Well, it solves the problem, but it creates another one. And that problem is when you calculate simply the amount of energy we received and the distance corresponding to this redshift, well, the energy has to be of order 10 to the 54 ergs, which is roughly one solar mass of energy. So we need to find a physical mechanism. Remember that it has to be small, okay, a few thousand kilometers probably, and the physics has to be such that in a very short time, and we're talking seconds, we transform one whole solar mass into energy. That's it. If you know something that can do that, you know something I don't know. All right? So there is really an energy crisis, and that crisis has been solved. An obvious way to solve it is to, as some people had proposed, is to put the energy, to make sure that the energy output is not isotropic, but is beamed, is directed in a very narrow beam. So instead of emitting radiation over 4 pi steradians, you emit over an angle, a cone with an angle of over a few degrees, and you gain at least 2 orders of magnitude and perhaps even 3 orders of magnitude on the energy requirement of the GRB. And indeed, that's what people have found. And one particular signature of a jet is what we call a break in the light curve. So these are light curves in the optical. So it's basically the brightness in magnitudes versus time. Note that all axes are logarithmic since its magnitude is log. And there is a decay rate here, and at some point there's a knee in the light curve, and the decay becomes steeper. And for that burst in 1999, we saw that there was, because of this strong break in the light curve, so these are the data from 2 groups, it brings the energy down to the level of order, where is it, 10 to the 51 ergs, which is of order of the energy involved in a supernova. So suddenly, the energy goes down, so we are somewhere between 2 and 3 orders of magnitude less than what we thought we would need. And so it is becoming feasible to have a very short event that is producing that amount of energy. Suddenly, it's something we can do. It's not easy, but it's something we've heard about. So very briefly, what we think the model is now, what we think happens is somewhere there's a central engine which will release a large amount of energy in a very short time, and that region is very small. Now, we don't know the details, but let's say magic happens, and for some reason, a jet is emitted. So the opening angle is actually less than what is shown here, but a jet, a lot of energy is emitted in a very narrow cone, and far from the star at a distance corresponding to 10 to 14 centimeter, so that's already a lot of solar radii. The burst happened. How does that happen? We think there are shells that are traveling at slightly different speeds. They are emitted at very, very nearly the speed of light. They travel at 99.9999% of the speed of light. These shells have small speed differences, and at some point, because of these differences, some will collide with others, and that will give the burst itself. And that's what we called the internal shock, because these shells are part of the burst itself. Now, at some point, these jet, it keeps propagating, and it will hit the interstellar medium, and it will light it up, essentially. And that's what happens here in the region of the afterglow, when the jet hits the interstellar medium, and that medium starts to glow. And it glows across the whole electromagnetic spectrum. And that's what we detect from the ground. That's the X-ray and optical afterglows I showed before, and that's how we can actually get a spectrum. And it glows all the way down to the radio. So that's really the toy model, what we think happens in a GRB. And I'm not going to go into the details of the physics of what happens here. It could be an entirely different talk. So I will try to focus on more trying to guess what we've done to understand what may be happening here at the center. Yes? Well, the reason why it shines is, when I say hitting, I really mean hit, as in hit, not heat. H-I-T, meaning that it slams into it. And what it does is that the material is going to be completely ionized, okay? And the emission mechanism we think is synchrotron radiation. So it's highly relativistic. Everything is ionized. There can't be any emission lines because, there's no recombination. It's way too hot for any recombination to happen. But in the spectrum, because it's synchrotron, it's a flat spectrum, or it's a power law. Now, the absorption lines are coming from the host galaxy, or anything that's in between us and the GRB. Any amount of gas that is, if there's enough material to produce an absorption line. So that's how, formally we can only put a lower limit. If all we have in the spectrum is this featureless synchrotron and a few absorption lines, the redshift is only a lower limit to the redshift. That's all we know. Now we can see emission lines sometimes, but from the host galaxy. I'll show a few examples later. And that's, very normal H2 region emission. All right. So how this supernova connection came about? In 1998, so it was suspected, now that we knew that GRBs were at cosmological distances, and that energetically they are sort of in the realm of supernovae, we thought that supernovae were actually a fairly good contender. And there was this event, 980425. The problem is, it was very, very close, and it was very, very faint. So people wonder, well, is that a regular GRB? The problem is that associated with it, there was a supernova. Since it was very close, the supernova was very well observed. This is the light curve. And it was what we call a hyper-energetic supernova, or hypernova. It had very broad lines. The expansion velocity of the material reached nearly 30,000 kilometers per second. So there was a lot of kinetic energy in that object. And it was a supernova of a type 1c, so it's definitely the collapse of a massive star. So at the time, many people thought, particularly theorists, thought they were vindicated, but many people thought that this was not enough because this burst was so weird. We had never seen a GRB at such a low redshift, and it was underluminous by several orders of magnitude compared to all other GRBs. And people were wondering, well, what is that? Does it fit into this picture of very energetic GRBs? Remember, over 10 to the 51 ergs. This one was about 10 to the 47 ergs. And that's, really, is it a different category? Is it just the faint end of GRBs? Some people, and actually many observers at least, were not too convinced that this was really the proof that GRBs were associated with supernovae. Here's a graph of spectra of different types of supernovae, just so everyone is on board. There are basically two types. Type 1As, which is the explosion of the white dwarf, and everything else is core collapse. And among the core collapse, there's those that have hydrogen lines in their spectra, those that have no hydrogen but some helium, and those, the type 1Cs, that have no hydrogen and no helium in their spectra. What that means is that we think there is the presence or absence of hydrogen and helium lines is basically it tells us something about the content of the envelope just before the explosion. And we think we need a Wolf-Rayet star, a star that has basically evaporated much of its envelope before the explosion, whereas a type 2 supernova, which does have, like this one, which does have hydrogen lines, still has a thick hydrogen envelope, and so there can be hydrogen lines when the star explodes and when the envelope is ejected. So, I think the event that convinced everybody that there is a connection between GRBs and supernovae came about in March 2003. So this, it has a redshift, 0.168, and so it's sufficiently far that it's really bright. In gamma rays, it fits really among the other GRBs. And what we could do, the afterglow was sufficiently bright that we could actually get a spectrum each and every night. And that's only a selection of these spectra here. And what we saw is that early on we see a featureless spectrum. These wiggles here in the red are just fringing in the CCD, and these little blips here, particularly this one, are emission lines from the host galaxy. And as time goes on, over a few days, we see the spectrum evolving. Remember, if it is cyclotron emission that powers the GRB, it should remain as featureless as this. Okay? It should get fainter and fainter, but there should be no feature. Whereas here, you see that the spectrum down here is fairly bumpy, and it is starting to look like the spectrum of a supernova. And indeed, if at these late time, and if we take this spectrum and we subtract a power law, as the energy distribution should be for synchrotron emitting source, then what we're left with is this spectrum here. And that is compared to two spectra of this SN1998BW that I just showed before, which was a type 1C. And you see that the features, even though the signal to noise is fairly low compared to these two, the bumps and wiggles are in the right place to convince us that this is indeed the spectrum of a supernova, of a type 1C supernova. So in this spectrum, actually, what we have is a power law, which is the GRB itself, and a supernova, both shining and both contributing to the total light. And two groups were working on that and reached absolutely the same conclusion. And we have dozens of spectra of this object. And we could show that the supernova associated with this event was actually very close to 1998 BW in terms of spectral features and its light curve evolution. So what we did, we monitored the light curve for a long time, and we need to model the light curve, and the sum of a supernova, which is here, and an afterglow, which decays according to a power law, actually reproduces very well the light curve, the observed light curve. So the spectrum looks like that of the supernova. The light curve is very similar to a supernova, so I think it's done. It's as good a proof as you're ever going to get in astronomy. So, and since then, things have moved. There's been several other events where we have very clear evidence for rapid evolution in the spectrum of the afterglow, and an evolution that can only be explained if there is a supernova component. And there's several of these objects here. So at this point, in early 2006, the main conclusion is this: gamma ray bursts always come with a type 1C supernova, a very energetic supernova. Okay, we think it's done. So we think we can take everything we know about core collapse supernova and apply it to GRBs in order to understand what is happening at the heart of the beast. Now, just a few words about their host galaxies. These are host galaxies of core collapse supernovae. So that can be type 2, 1b or 1c supernovae. If I ask you to look for a grand design spiral, it's very easy. There are several to pick. If we look at the GRB, nope, where is it going? If we look at the host galaxies of GRBs, also observed with HST, if I ask you to find a grand design spiral, it's going to be much harder. It's going to be hard-pressed to find one. Okay? And the reason is that the host of GRBs are essentially irregular dwarf galaxies. In other words, they're faint. They're definitely not as bright as our galaxy. They're sort of LMC-like, even fainter sometimes, and they're very irregular. For those that are at low enough redshift that we can do, we have a good morphological information. If you look at something like this, for instance, there are several bright knots or blobs, or call them whatever you want, but there's no structure. There's absolutely no sign of structure. So that's obviously why they are irregular. But basically, they are fainter and smaller than those of most core collapse supernovae. There's been a bit of progress made. With a larger sample, we can make such comparison by looking at different subsamples of supernovae, type 2s, type 1b, and 1cs. And it turns out that this plot is essentially the fractional flux that's inside. If you look at where an object happens in a galaxy, a supernova or a GRB, and you integrate the light inside the radius to the supernova or GRB, and then you compare that to the total magnitude, and that gives you a number between 0 and 1. Okay? So 0 means that the object is on the brightest pixel. Okay? There's nothing beyond the pixel where the GRB or the supernova is. And 1 means that the object is far out. And when we look at where GRBs fall in their host galaxies, they compare very well with type 1c supernovae. If you look at, so the GRBs are this black line here. The type 1c supernovae are this green line. But if you look at type 2 supernovae, it's this blue line that goes nearly in the middle. What this line means is that a straight line going from 0, 0 here to all the way to 1, 1 here means that a class of object would actually trace the light. In other words, if you think of these galaxies as being exponential disks, it means that for type 2 supernovae, they have their distribution is exponential. It follows the light. Now, for these objects that are below here, those type 1c and GRBs, it means that they are more concentrated than the light. In other words, it means that they want to fall very close to the brightest pixels. That's essentially what it means. So type 1c supernovae and GRBs this reinforces this association because they want to be very near the bright pixels in their host galaxies. And that's another clue. It tells us something that among all the supernovae, the GRBs have something intimately in common with those that lose a lot of mass, because we think that type 1Cs, they have to lose a lot of mass to evacuate all the helium and hydrogen that we just don't see in the spectrum. Now, why would there be such a difference? For a while, we've been thinking that metallicity was a very good culprit. The host galaxies have a very low luminosity, they're irregular, and by virtue of the metallicity-luminosity relation, they should be, statistically at least, they should have fairly low metallicities. And for those cases where we can actually measure the abundances from the emission lines of the host galaxy, we find that it's fairly low. It's a fraction of solar metallicity. And also theory says that it's easier to produce a black hole at low metallicities because we do want the star to lose mass because we do want to evacuate the hydrogen and helium, but we don't want to lose so much mass that we wouldn't have a black hole. From energetic considerations, we think that we need a black hole. When a massive star collapses, it will form a proto-neutron star that may or may not become a black hole. And we do think that we need a black hole, so we need that neutron star to grow in mass and eventually become a black hole before anything really relevant for the GRB actually happens. So it may be that gamma ray bursts, because they come from very massive stars, they trace the star formation rate across the universe, but it is definitely a biased view of the star formation history of the universe. And for a few years, people have been hoping to use GRBs to, trace the star formation history of the universe. Suddenly, we knew that there would be a significant bias in this view. Although one could say that as you go to higher and higher redshifts, hopefully statistically, galaxies are more and more metal poor, and we have a chance of tracing the star formation history at very high redshift using GRBs. Now, in contrast, supernovae 1c occur at all metallicities, and if anything, they tend to occur rather in more metal-rich galaxies. So what do we think where are we in terms of progenitors? What do we think we know about progenitors? The leading model is what we call the collapsar. Basically what it is a very massive star that has some rotation. Remember, a supernova is a nearly spherical explosion. A gamma ray burst is highly beamed. So if you want to go from a star that's nearly spherical to a GRB that has a beam, you need a way to break the spherical symmetry. An easy and almost obvious way to do that is with rotation, because it provides a preferential axis. And that is, that's where this collapsar model is based on. And it could be either a single star that is rotating very fast, or it could be a binary that has merged and where some of the orbital angular momentum is being absorbed by the merger product. So what we need to do, nevertheless, is we need a high amount of angular momentum, and we need to keep that angular momentum, at least in the core, because that's where the GRB is going to be born. We need to keep that angular momentum in order to break that spherical symmetry. So it means that we have a kind of a problem. We want to lose a fair amount of mass. We want to lose the mass, a fair amount of the mass in the envelope because we want to get rid of hydrogen and helium. But we don't want to lose too much mass, because the problem with mass loss is that it also carries away angular momentum. And we want to keep the angular momentum, or at least a fair amount of it. So there might be some fine-tuning going on in order to produce a gamma ray burst. And we think that the progenitor is a Wolf-Rayet star, so at the very end of the evolution of a massive star that has very strong wind and has lost its hydrogen and envelope. And after the core has collapsed, for perhaps a few seconds or maybe a few minutes, an accretion disk will form, because matter won't fall straight down onto the black hole because of the angular momentum. There'll be an accretion disk, and the black hole will accrete matter. And this is where the magic happens. Somehow a jet will be formed and will eventually propagate into the star, break free, and continue to live a life of its own. Now, how is that jet launched? We frankly really don't know. You can guess that magnetic fields and neutrinos are probably going to play a role, or at least we need to quantify what role they may play. But it's going to be, it's certainly a lot of very complicated physics happening down there, all that at temperatures of billions of degrees. So I leave that to theorists. I'm just an observer, and I count photons. I can definitely not go into that kind of territory. But the question remains how we can get to that point where we lose some mass but not too much. We we want to keep some angular momentum. There are ways. One possible way is for a very massive star to evolve quasi-homogeneously. Some people can make models like that in the computer. It could be, we don't really know if the progenitor is a single star or can it be a binary, just two very massive stars that are close to each other, and at some point, and the orbital parameters are just tuned so that they emerge not too long before one of the stars go supernova. And we have no idea of the role of the magnetic field. Magnetic field in general in the evolution of stars is bad news as far as rotation is concerned, because magnetic field will sort of lock the core and the envelope of the star. So when the star loses mass, the magnetic field will make sure that the angular momentum is pumped out of the core. So we need a very, very strong magnetic field to produce the GRB itself, but maybe it's produced in situ. But we're not sure what the role of the magnetic field is going to be during the evolution of the progenitor itself. So these are some of the open questions that we're facing. And this is just a diagram showing at 4 different metallicities. This is the mass of the initial mass of a star between 10 and 60 or 65 solar masses, and the vertical axis in all 4 plots is some measure of the rotation rate. It's the amount. It's related to the amount of angular momentum. So stars here near the top rotate very fast, and stars here are just not rotating at all. And at these 4 metallicities, you see several regions that are coded according to the end product, whether the object forms at collapse, it forms a black hole and becomes a type 1b or 1c supernova, or a type 2, or a type 2 with a black hole as the remnant. And according to theory, you see that when the metallicity gets lower and lower, the region where GRBs can live gets larger and larger. And we think that there should be lots of GRBs, at least according to theory, there should be lots of GRBs at very low metallicity for a wide range of masses, but the requirement is always that there is a lot of angular momentum in the core. And you know, what people would be trying to do, not only in the field of GRBs, but supernovae, is to basically populate this diagram and to put real events in there. In other words, be able to determine the mass of the progenitor and, if possible, the rotation rate. So we can have an observational version of this plot, and so we can test it. Okay, so we think we've solved a problem. GRBs are associated with supernovae. That's a done deal. If you work on GRBs, it means you work on supernovae and vice versa. Well, here come 2 events in 2006, whose light curves look like this. So 60505, 0624. This is the afterglow. The black dots are the afterglow. It was detected after a few hours, and after a few days, well, these are without error bars, or maybe you can't just see them. These are upper limits or actual measurements of the brightness. These colored points are what these various local supernovae would look like if they had been at the redshift of this object. Okay? And you see that the afterglow is nothing like these supernovae. That's the brightness we should have measured if a supernova like 98VW had been at this redshift. And there's nothing. And the same happens for this event about a month later. You see that the afterglow is better sampled. We see it decay, and here we're hitting basically the host galaxy. And same story, we're not seeing a supernova. If there had been a supernova like any of these 3 at this redshift, 0.125, then the afterglow should have a magnitude between 20 and 22. There's nothing. So if there is a supernova, it is very faint. So suddenly we have a problem. We thought GRBs were associated with very luminous, very energetic supernovae. Well, no, they aren't. And yes? Yes. Yes. Yes, but you need to feed the accretion disk at some point. You know, remember that at some point the whole star will be blown up. We don't really understand what happens to the accretion disk. Will it stay there, and will there still be matter being accreted, or will it be blown away? We actually think that the accretion can go on for a fairly long time, and long time in GRB world may mean hours, if not days, because with the Swiss satellite, we've seen that there is now evidence of refreshed activity in the GRBs. It's not, if you want, it's not a second GRB, but we see some structure in the X-ray light curve in particular that are indicative that there is still something going on in the central engine, but we don't really know exactly. That it might not have a supernova, but this refreshed activity, we think it can last a few hours, a few days perhaps. But here, if there had, imagine in that particular case, if there had been a supernova going off, say, if the real GRB had gone off, say, a week before, and this is a second GRB happening here, and this is the afterglow, then, the supernova associated with the first burst should have been visible here. Anyway. Now, if the time scale becomes sufficiently long, then it is possible, but I'm not sure. There used to be a model of this delayed supernova explosion, but the thing is, for all the supernovae we found associated with GRBs, we think they exploded within the same time, say a day or two of each other. And that's as good as we can time the explosion date of a supernova. So that's not impossible, but it would take, some really fine-tuning of the central engine. And for an accretion disk around the black hole to survive for a very long time and to have, for the energy in the burst to be comparable to the energy of all other bursts, I don't know if this is possible, if the disk can survive for such a long time and could suddenly start accreting again and produce a burst. I have no idea. Okay, then here comes, we were at the point where there are GRBs that have no apparent supernovae. Well, not all is lost, perhaps, because in 2008 this supernova went off, and 208HA, it is hopefully a type 1c supernova. And here is, where is it? Here is the actual light curve of this supernova compared to a few other fairly bright supernovae. And you see that it is several orders of magnitude below in luminosities. Now, looking at the light curve of one of these GRBs I showed in the previous slide, 060614, which is this one, the afterglow decayed, and then we hit the host. If that supernova, this one, had exploded at that distance, at the distance of this burst, it would have looked like this. So it would have been hardly a little blip here on the light curve. Okay? And it seems that theorists have no problem making a supernova that faint. It is possible to make a supernova that produces virtually no nickel 56 during the explosion, and hence the supernova won't shine or will be incredibly faint. So it may be that there is a type of 1c supernovae that can be sufficiently faint to explain the absence of supernova in this particular burst. Some people say that this particular supernova is actually a type 1a. Well, I'll leave it to the supernova specialists to decide that. But at least the possibility exists that we can make a GRB still with the collapse of a massive star, but sometimes there is a bright supernova and sometimes there isn't. well, of course, it complicates things because we've got to find mechanism to make a bright or faint supernova. But at least we can stick to that, can try to stick to having a simple model with massive stars involved rather than start looking for very different types of progenitors. Now, I've said that the difference between supernovae 1c and GRBs was caused by metallicity. That's what I would have said a few months ago, perhaps even a few weeks ago. Problem is, according to theory and according to what we've seen so far, there should be no GRB in a galaxy with a metallicity about half solar, larger than about half solar. Now, the problem is, 2009BB, a supernova that exploded earlier this year, it turns out to be, it's a fairly bright type 1c supernova in a very metal-rich host galaxy. Nothing wrong so far, okay? Problem is, it is also incredibly bright in the radio. Now, what does that mean? Compared to other type 1c supernovae, it's orders of magnitude brighter in the radio after a few weeks. And it is just about as bright as a GRB in the radio. Meaning, what has very likely happened in this case is that there might well have been a GRB, but the jet was oriented away from us. It was pointing away from us. We didn't see the burst of gamma rays itself, but we see the late-time radio emission, which happens essentially when the jet has decelerated and the emission has become not beamed anymore, but isotropic. So we can see the radio emission from all over the sky. Okay? It's isotropic, which is why we see it now in the radio after several weeks, but we didn't see the burst of gamma rays. And that object in radio was very bright, as bright as a GRB, much brighter than a type 1c. That's a pretty serious indication that there was a jet, that there was relativistic emission associated with this GRB, this supernova. So metallicity suddenly becomes less of a contender for explaining the difference between type 1Cs and GRBs. It may well be that high metallicity environment can produce GRBs. Otherwise, if that is not the case, we still have to find an explanation for the very high radio brightness of this supernova. What can it be? I don't know. But what it also means, incidentally, is that if you thought we were safe from GRBs because we are in a high metallicity environment, well, maybe we're not so safe because a GRB could go off in our galaxy very soon and we have no idea about it. And we can only hope that it's pointing away from us. All right, I will try to conclude and show, what questions we'd like to answer. So first, basically, why? Maybe I could have said that on my first slide. Why should we care about this whole thing? The supernova is the only way we have to constrain the progenitor. If you, as I said, the jet happens and then it lives its own life, and the GRB and the afterglow emission happen very, very far from the progenitor because it's traveling at relativistic speeds. And the jet basically forgets all knowledge of the parameters of a progenitor star. If we want to know what the star was, its rotation rate, its mass, its rate of mass loss, or what exactly can produce a GRB, what type of star can produce a GRB, we have to constrain the supernova because that is the only way to constrain the progenitor star. We can model supernovae by using spectra and light curves. We can't know anything about the progenitor star by using the GRB light curve itself. Now, this question of, is there always a type 1c supernova associated with the GRB? Well, possibly at some point. There is, again, from radio emission of supernovae and GRBs, a lot of type 1bc supernovae have been monitored, and it turns out that there's only a very small fraction of type 1c supernovae that have a GRB. In other words, whatever produces a type 1c supernovae, only a small fraction of them, we're talking 1 or 2%, a few percent at most, can produce a gamma ray burst at the same time. So most of the other core collapse explosions will not have a GRB. Now, are all these supernovae hyperenergetic? Again, we thought yes early on, but maybe cases like 060614 are a warning. We're not too sure, but in any case, there are too few cases to tell. We still have only 5 GRBs, supernovae, with very good spectroscopic monitoring, so that's still very few objects to do statistics with. Now, the more general question, is there always a supernova? Well, it was a model. It was a strong contender early on. We thought we got to the point where we could say definitely yes. Well, then, in 2006, we had to say no. And then, possibly, because of this 20HA. So, frankly, we don't really know where we are at this point. It might be that this supernova GRB zoo is a lot more complex than we thought. And what we really need to understand in order to understand this variety of relative GRB at supernovae brightness is what determines this branching. What is it that makes one star go off as a GRB and a supernova, while most other massive stars, the overwhelming majority of massive stars, just are happy to explode and leave probably a neutron star behind and have nothing to do with GRBs. We really don't understand what determines that. We thought rotation would play a role. We thought metallicity would play a role, but exactly what? And is it some interplay between these parameters? And is there yet something else that we don't know about? Frankly, we don't really know where we are. And I didn't say much about this, but there is a graduation in the some kind of ranking or scaling of gamma ray bursts of these explosions, going from full-fledged gamma ray bursts to X-ray rich gamma ray bursts that have a lot of X-rays at the same time, to X-ray flashes, which have essentially X-ray emission. They are bright flashes of X-ray emission, but very little gamma rays, and maybe all the way to normal supernovae. X-ray flashes and X-ray rich GRBs, they are part of the GRB family, but we'd like to know what determines this continuum, this change in the high energy properties of the burst itself. Is it related to the mass of the progenitor, the history of mass loss? You can think of whatever physical mechanism you're able to put in your model of stellar collapse and black hole accretion. So a while ago, I had produced a plot like this, trying to simplify things a little bit, where this is essentially the energy in the supernova versus the energy in gamma rays, the energy in the burst themselves. So there's full-fledged gamma ray bursts for which there is obvious evidence for a supernova, like 030329. And there are X-ray flashes that are a bit less strong, where there is also evidence for a supernova. And there are very weak events, like this 980425 I mentioned early on, but with a bright supernova, or this object, 080109. I didn't have time to talk about it. And below that, in principle, at high metallicity, so this is low metallicity, this is supposed to be high, we should have standard type 1c supernovae and no GRB. Then there are events like this, where there is a GRB, but apparently no supernovae, no supernova associated with it. So maybe that event, 208HA, that supernova, helps us explain why this object had no apparent supernova. Maybe it was just a very faint one. So maybe that is not so much of a problem. But the new problem is this supernova 09BB, which happened in a very metal-rich environment, and which seems to have a jet associated with it. So it had a jet which was expanding relativistically, and later on became non-relativistic, and we saw the radio emission from this guy. So I had written a few weeks ago that it is tempting to try and see a diagram like that as sort of, you know, simplifying things with this new objects here. I think I have to put that sentence in the past tense because clearly we don't know what determines the difference between a GRB and a supernova. And I have to admit, I have no idea what, if it's not metallicity, what can explain the difference. It's probably a complicated combination of metallicity, mass loss, history of mass loss, the angular momentum, and then you can start playing with binary stars and putting some magnetic fields, and there's no limit to the imagination of theorists. The problem is, I think from a theoretical point of view, we're still very far from understanding what is going on in a plot like this. And observationally, we clearly need a lot more objects in order to really understand whether objects like this or, whether an object like this or like that are red herrings, or if they are really serious clues that we should take into account. So that's the final sentence that an observer has to say: we need more data. Obviously, we need a lot more objects in each of these different categories in order to be able to see clear when we classify these objects, in order to understand this connection. Thank you.
Thank you very much. Now we have some time for questions. So, yeah.
I would like you to comment on one of the few graphs, right? The one that you saw, the dichotomy between the short-lived one and the long-lived ones. Mm-hmm. Isn't that an observational bias? Because typically it would be more difficult to see the short-lived ones, while the long-lived ones would be easier to observe.
Why would it be harder to see? Why do you think?
They last very, very short time.
Yes, but the shock. The short, the shock that happens very quickly is the GRB itself. The thing is, they're detected by gamma ray satellites, which usually have a very, very large field of view. We're talking a significant fraction of the whole sky. So, Swift, which is in the air now, has 2 steradians, and that's 1/6 of the sky. So it is easy in a sense to see GRBs because the field of view of gamma ray observatories is very, very large compared to the field of view of any optical or radio telescope, any telescope on the ground, or most telescopes on the ground. So that's why it can be fairly efficient. And there are instruments that are literally monitoring the whole sky. The gamma ray burst monitor on Fermi is seeing almost literally the whole sky, as far as I know.
Any more questions?
Sorry if this question, it has not to do with what you have been speaking, but it has to do with gamma rays at least. You probably are aware about this observation of the gamma rays arriving at different times. And there is a magic observation in La Palma, I think 4 years ago, saying that the high energy gamma rays arrive later than, at least I think it was something that 20 minutes or something like that, minutes later than the low energy gamma rays. Is that true? It has been confirmed in other observations in satellite and so, because that would mean it would have important consequences for the structure of even, I don't know, for relativity even.
I don't know if it's been seen for other bursts. I'm not sure. The thing is, my personal bias is more towards what's happening in the optical with the afterglow. What's happening in the burst itself and at high energy end, I leave that to people who do that and to theorists who try to understand it. Now, the thing is, for most bursts where, pretty much we think all the photons arrive at the same time, it turns out that the high-energy energy photons tend to arrive a little earlier than the low-energy photons. Well, that's what we see for most bursts. Now, for that burst you mentioned, maybe there was some kind of refreshed shock or continuing central engine activity. that has been able to produce some very high energy emission. But how is it possible to do that? I don't know. I guess this is another of these events where people are scratching their heads and wondering, is it something that's typical? Can it happen in any burst, or does it really take something very, very special, as in several cases I showed here? Some people a long time ago someone said, when you've seen one GRB, you've seen one GRB. So, there's a wide variety of behaviors, and even if all you have is a gamma ray light curve, you can probably explain what you see, even very delayed high energy emission, with by fine-tuning a particular model. But how to do it, I don't know.
Anyone else? Okay, I do have a question. I might have not understood it, but you said that the light curve of the afterglow was usually the GRB light curve was the addition of the afterglow plus the supernova. Does this apply for both the long and the short GRBs?
Oh, well at late time, when we see, when we monitor the decay, there are these two components, we think. For short GRBs, it turns out that ever since people have found afterglows for short GRBs, which happened only in 2005, they have obviously looked for a supernova and have never found any. At least for long GRBs, we found supernovae in most cases. For short GRBs, there's never been a supernova. So we think that in the case of the afterglow of a short GRB, there's just that, the afterglow. That's it. There's no supernova.
Anyone else? Okay. Are you staying for lunch?
Yeah, I'm
if you're
around.
interested, then you can have lunch and talk to him. And I think we should thank him again. So.
Okay.